Crime. It's an unavoidable aspect of any city. While there will always be well-intentioned attempts at reducing the number of incidents, nobody can ever expect crime to completely vanish. Our project focuses on the city of Charlottesville, a college town situated in central Virginia. There are several resources offering general statistics for crime, but these studies don't consider patterns or commonalities between incidents. For example, are burglaries more common in wealthier neighborhoods? Does vandalism happen more frequently on Friday nights, when college parties are often held? Furthermore, are some incidents of crime like robbery and theft more similar than others, like arson? Our project aims to use machine learning to cluster offenses based on features such as time, location, and demographics. Ultimately, we hope to shed light on the underlying patterns of crime and help make Charlottesville a safer city for everyone. The data to be used are provided by the City of Charlottesville. There are very specific sets that will be incorporated into our analyses, including those on crime, arrests, and demographics. The crime data set is updated every evening and as of 9 p.m. Eastern Time on October 14th, contains information on 29,000 incidents since October 15th, 2014. The dataset on arrests contains 17,000 entries beginning on the same day as the crime data and is similarly updated on a daily basis. So how exactly did we analyze this data? Data points that were deemed non-crimes were removed from consideration. They were then grouped by hand into 7 overarching categories: assault, disorder, driving, drugs, fraud, sex, and theft. A k-means clustering algorithm was applied to the data. Here are the geographical locations of the clusters, identified by their color. Qualitatively looking at the plots and considering the inertia graph, we see an elbow for k equals 5. Thus, it is best to conclude that the best separation occurs when the data is divided into 5 clusters. Cluster 2 has a notably higher frequency of assaults, with the cluster's mean sitting at 0.25 out of a possible score of 1, compared to the total dataset's average 0.15. On the other hand, it has a lower frequency for theft with 0.17 versus the total dataset's 0.28, and for fraud with 0.02 versus 0.06. Cluster 3 is also notable for having a higher frequency of theft of 0.34 compared to the total average of 0.28. Let's move on to the arrest data. Some arrests, deemed irrelevant, were ignored, such as littering. The following diagram depicts the k-means clustering of arrests purely by time of day. The number of arrests seems to be somewhat more concentrated during evening hours, between approximately 5 a.m. to 5 p.m. Crimes were then grouped based on the offender's race and gender, as well as the category their offense falls under. 9 categories were used: crimes against morals and decency, against the administration of justice, against a person, involving health safety, involving fraud, against property, against peace and order, involving motor vehicles, and involving alcohol control. These groups were inspired by the Code of Virginia, Title 18.2. Based on the silhouette and inertia plots against a number of clusters, the data is best divided into 11 groups, one of which was thrown out due to no weight being assigned to any of the features, resulting in effectively 10 clusters. This table indicates the most common occurrence within each feature for every cluster. Thus far, we have shown the resulting clusters that our machine learning algorithms have produced on the crime and arrest data of Charlottesville, Virginia. While interesting patterns have already begun to emerge, we plan to further examine the distributions within these clusters and hope that they can give us a better idea of the characterization of the city's crime and arrests.